Hey, welcome back. Today we're going to be talking about Universal Gravitational Potential Energy for AP Physics C Mechanics. And I want to start with what we already know. So what do we know about gravitational potential energy on the Earth? Well, we know on or near the surface of the Earth that if you were going to lift an object from an initial position to a final position, there would be a change in potential energy. And usually we would write this as PE, but in terms of AP Physics C Mechanics, we would write that with a capital U. And that would be mgh, would be the equation for that. That's on or near the surface of the Earth. There are reasons why that is reduced to that we're going to get into. But I also want to use this equation here to think about why that is. So you could say it would take work to be able to move that object from the initial position to the final position near the surface of the Earth. I probably should have drawn the Earth much larger, but you can think of this as the integral of the force with the dot product of dr. And that, in this case, would be equal to the change in potential energy of the system, so to speak. So there's external work being done, and that work is going to change the potential energy of the object that we lift up. Now we can do some substitution in here. We can say we're going to have to overcome the force due to gravity. And so we could say, well, then that would be mg times dr, right? And this right here, this is a dot product. And really that's focused on the force that's in the same direction as the motion. In other words, the dr tells us that we're integrating with respect to infinitesimally small units of r, but it's the force that's in that same axis. Let's call it the positive y-axis or negative y-axis. In terms of the y-axis is what we're talking about. So it kind of goes away here in the sense that there's no x-axis forces to worry about. Now this dr we could call dy if we want to. It's actually up to us. And then down here we're going to start from 0. We typically do that where we set our height equal to 0 at the lowest point for a conservation of energy problem on the surface of the Earth. And we could say that this is some height as you go up, right? So yeah, let's sub this in. We'll just call this mg dy over here, where this is height and this is our 0 value. Now we could continue with this and we would say, all right, that's going to be m and g are constant, and this is really important that we're going to come back to later, but this is dy here. So we could say our work is equal to mgy evaluated from 0 to h. So from that we could say, well, effectively the work that's done, which is going to be equal to the change in potential energy, is going to be equal to mgh here. So that's how we can justify getting mgh, but it's really crucial that we point out that this is constant right here. And that's the reason why we can pull out the m and the g, is because near the surface of the Earth, the mass and the gravitational acceleration is not going to change. Mass doesn't, but what's important to notice is that the gravitational acceleration is 9.81 meters per second squared. Now, as you get farther away from the Earth, though, it's actually not constant, so it's a problem. So we got to think about, all right, well, how would we approach this if we're talking about the Earth in a system where the gravitational acceleration is not constant? Okay, and so let's say we're going to do something similar here where we have an object, but in this case, we're actually moving some distance that's significant away from the Earth, where it's actually being moved farther from the Earth, where we can no longer assume that g is constant, because it's important to realize, like, the farther away you get from the surface of the Earth, the less the gravitational pull on objects is. And this g is no longer constant. So let's think about how to approach this kind of problem. We want to do this in a more universal way. And we happen to know Newton's universal law of gravitation. In other words, this distance in between here, we could call this like r1, and we could call this distance r2. These two r values are going to be significant enough that the gravitational acceleration does not equal 9.81 meters per second squared. And we want to think of this in a more general sense, in a more universal sense, actually, anyways. So let's think through how to approach this. We could still say the amount of work that's needed to be done to do this is similar to what we had written before. dr, this is like our general equation for the amount of work that needs to be done to make this happen. But now the force due to gravity, this is not constant, and we want to make it universal. make it universal in the sense that we're not just talking about the surface of the Earth. We want to do something more meaningful with it. And one way we can do this is we can say, well, that work is going to be equal to, now let's use Newton's universal law of gravitation for this. So that would be like the mass of the Earth times the mass of the object, times g, can't forget g, over r squared dr. And we could say, let's take this from like r1 to r2. And that would be, in a way, we could measure the amount of work that's done on the system to move the object from position r1 to position r2. Okay, well, let me clean this up a little bit. First of all, we can pull out of the integral anything that is a constant. So g is a constant, the mass of the Earth is a constant. Actually, the mass of the object is also a constant. So let's think about what's left. We are left with just 1 over r squared dr, where we're evaluating from r1 to r2 over here. Well, 1 over r squared, that is equivalent to r to the negative 2 power, just to remind you of that fact. So if we integrate this, we end up with a negative out in front and a 1 over r here, and that's going to be evaluated from r1 to r2. And what does that lead us to? Well, that leads us to this. So the amount of work done, or the change in potential energy, would be equal to this scenario. Alright, so that helps us to understand what's needed to take something from, say, the initial position to the final position over here, or from r1 to r2, in a case where the force due to gravity is not constant because we're far enough away from the Earth that we cannot use mgh. But we want to take it one step further because we do end up with this equation right here. And the question is, how do we get this? And we're actually very close. So I'm going to move the screen so that we can continue over here. I can get a little more room. There are a couple really big assumptions. So to be able to generalize this, we need to have a reference point. So when we do a problem like with MGH, usually our reference point is going to be the lowest point that we have, like the floor or the bottom of a ramp or something like that. That's where height is going to be equal to 0. But it's really crucial at this point to remember that height can be marked as 0 wherever we choose. It's just an arbitrary marking. To generalize, if we set our reference point, instead of at the bottom of a ramp or the bottom or the floor of a room or something, if we set the reference point at infinity, this may seem a bit odd at first, but there are some good reasons for this. Then we can say that our R initial is equal to infinity. Okay, so what does that do for us? Well, if we look at our previous work that we have down here, in this case we could call R1 equal to infinity. Well, what is anything over infinity? Well, that's going to be equal to 0. Anything divided by infinity is actually equal to 0. So check this out. We are left with the work that's also equal to the gain in potential energy is equal to minus g. We can write it in the format that they're using, times m1 times m2 over r. And this is on your equation sheet. Or you could say the universal potential energy equation is this, minus g times m1 times m2 over r. That's going to be its universal potential energy. Now, I really want to make a couple points here and show you a couple other things because this is a bit confusing. I want to emphasize the negative sign that you see right here comes from the derivation, and it also comes from the fact that we're going to use infinity as our reference point right here. So those two ideas give us the negative value that's embedded in this. And the other point I want to make is there are actually two good reasons why we want to set our reference point at equal to infinity when doing these things. One reason is because we want the infinite distance for the force due to gravity, universal law of gravitation equation. That's this. Let me write that down really quickly. That's this right here, universal law of gravitation. We want this. If this r squared value is equal to infinity, then we want the force due to gravity between the two objects to be 0. Just like, in a similar way, we want the potential energy to be 0. For universal gravitational potential energy. So both of these we want to be 0 at an infinite distance between the two objects that we're talking about. That's crucial. The other thing that's crucial is if you think about it, there really isn't any arbitrary 0 point in the universe, other than you can do it mathematically with infinity. In other words, you can't make like the surface of the Earth where you're standing, for instance, to be our 0 point where everything else is a reference to. because that's constantly in motion, depending on what your frame of reference is and what you're comparing that motion to. So we just have to roll with it. Okay, I want to show you two other things really quickly. Okay, so I want you to think about this. We just derived this equation that you see over here. I want you to, how do you think about this? So let's say we have two masses and they are an infinite distance away. Let's say this is infinity here. If that's the case, then our amount of potential energy, you could say UG, is equal to 0. But if you say that they are not some infinite distance, we could call it like R sub A or something like that. That is going to have less potential energy. So we're going to have less UG. So you could say it's more negative than 0. So if 0 is the greatest value we can have for our potential energy, this is the greatest value for universal potential energy right here, then this is going to be less, this part right here that I'm talking about for A. Scenario A is going to be less than 0. And that makes sense if we have a negative sign in the equation and we define infinity as where you have the greatest potential energy. Because if you think about it, it takes work to separate these objects. They attract each other. If there's something like planets, imagine they were close together, they would have a great attraction amongst each other. So to separate them, you have to do work. If you separate them to an infinite distance away, then the potential energy, universal potential energy, is going to max out at 0. And if we have a scenario like this, where we're talking, let me clarify, these distances should be between the center of both objects. That's always how we're looking at this. So this is going to be the distance between the center of these two objects. The center of these two objects over here, that's an important idea, not to the surface. So if we think about the distance to the center of these two objects over here, let's call this radius B over here, then what kind of potential, universal potential energy are we going to have here? We're going to have even less potential energy here. So that means we're going to have even more negative potential energy due to gravity. So more negative than 0. This we could say in scenario B. This is scenario A and this is scenario B. We could say in scenario B, we've got even more negative potential energy than in scenario A. So that's how you could think about this. And notice that as we go up from the bottom example to the top example right here, this is gaining energy, gaining potential energy due to gravity, you could say. So that's how to think about this. It is true that there's a negative sign here that you cannot ignore. It's very important to think about. Think about the distance being infinity. One more thing, notice that there is no squared value in this equation right here, and I have just shown how that comes about. It comes about because of taking the integral of Newton's universal law of gravitation and the implications of that. So hopefully this has been helpful. I've done lessons on an entire year of physics, as well as most of the ideas for AP Physics C mechanics. If you have any questions or comments down below, please let me know, and I hope you all have a great day. Take care.